Hi everyone, welcome to ML++ with Omkar. In this video, we are going to tackle a very interesting puzzle named Antipodal points. This puzzle has been picked from this website Brainsteller, which is a collection of really great puzzles ranging from basic mathematics to probability to discrete maths, so on and so forth. Feel free to give it a try. Now, this puzzle, I personally find it interesting for the reason that it has a very generic appeal to it, but in the end, in order to solve it, we really need to use some fundamental concepts of mathematics, which really goes to show the power of mathematics, even in practical scenarios. I mean, I say even in because we know mathematics is meant to understand the world, but there is this idea that maths is really more abstract and theoretical than it is practical. So, this is one of those problems which kind of closes that myth altogether. Now, the question says, prove that there are two opposite points on the Earth's surface that have the same temperature. Fair enough. We just need to prove that there are 2 points which are like, so when they say two opposite points on Earth's surface, of course they have to be diametrically opposite. They have the same temperature, and by the language, it means that at least one such pair should exist. Assume that the temperature varies continuously over the surface. Now, this is a big giveaway because when they say that temperature is varying continuously over the surface, they are basically saying that temperature can be considered as a continuous function. Now, with these two things in mind, temperature has been given to us to be a continuous function along the surface of Earth, and we need to prove there is at least one pair diametrically opposite such that they have the same temperature. Let's get into solving this problem. All right, let me open the notebook. Yep, we have other tabs open. Yeah, okay. So now, before going ahead, if we think about two diametrically opposite points on the given sphere, we must imagine circles which is exactly cutting the sphere in half. Take a moment to pause and think over what I just said. You are imagining 2 points which is completely like on diametrically opposite sides of the given sphere. I don't have a sphere right now to like visualize it. Otherwise, it would have been really easy to visualize. So, anyways, I mean, just imagine you have a sphere. You are talking about two diametrically opposite points. So when you draw a line, let's say like uh, which basically connects point A to point B, it has to split the sphere in half, right? In other words, we need to consider two diametrically opposite points on circles which cut the sphere in half. And please note that there will be infinitely many such circles, right? So you have a sphere, you can literally rotate it in any angle and create circles which exactly cut the sphere in half. Just think about it. There will be infinitely those many kind of circles which will cut the sphere in half. In any one such circle, we need to consider and we need to prove that two diametrically opposite points have the same temperature. So for simplicity, let's just consider a circle, right? So from a sphere, we have come down to circle for obvious reasons, because if two diametrically opposite points are lying on any sphere, they of course have to lie on some circle which is equally cutting the sphere into two halves. This is more of a visualization. It's unfortunate that I don't have a sphere right now to clearly demonstrate it, but you can think about it. That's how it is. So we have some circle on the given sphere, and that is cutting the sphere into half. And on that sphere, we'll of course have to assume 2 points, and we'll have to show that they'll have the same temperature. So let's assume some temperature T as a function of theta. So let's just say, for sake of fun, let's say this is equator line. Of course, that might not be true. Uh, in fact, let's not say this. This is very misleading. This will go into geography and all. I don't want to go there. So this is some reference point, right? This is some reference point. And so at an angle of theta, let's say the temperature is T theta. Right? So just imagine one circle which is cutting the earth into two halves. You are covering a distance of theta from some point of reference, some x-axis assumed uh, on the circle, for the circle as a frame of reference. And at an angle of theta, you have a temperature of T of theta. Now, what we want to prove is at t of, so this is theta at theta plus pi. So this is theta plus pi. The temperature will be T of theta plus pi. We want to prove that there exists some theta which belongs to 0 to 2 pi such that T of theta is equal to T of theta plus pi. This is what we are supposed to prove, right? So in a nutshell, this is all we want to do. We want to show there is some angle such that this condition holds true. Now, the moment we see this, we can actually do something. This should remind us of something familiar. So, whenever we want two things to be similar, we usually work on the ideas of difference functions. Now, please remember they have said that t is continuous. So, t of theta is a continuous function. That means t of theta plus pi, of course, this is the same function. This is also continuous. Now, we know that addition of, like, linear addition or subtraction of two continuous function will also be a continuous function. So if I consider some difference function g of theta, define it as t of theta minus t of theta plus pi, this is also a continuous function. Right? This is just a linear property of how functions work. If two functions are continuous, any linear combination of those two functions. So in general, it's like if you have f of x and g of x, then some a times f of x plus b times g of x, where a and b are constant coefficients, this will also be continuous, given that these two are continuous functions. That's usually how it goes. So if I consider this difference function, again I'm considering a difference function because I'm supposed to prove these two things are equal. In other words, t of theta minus t of theta plus pi needs to be 0. That's why I'm going towards difference. So if I define a function called g of theta, which is this is also a continuous function, right? Now, g of theta is this. How will the difference look like at g of theta plus pi? At g of theta plus pi, this is t of theta plus pi minus t of, so theta is replaced by theta plus pi. So theta plus pi is theta plus 2 pi. Remember, theta plus 2 pi, this is theta, theta plus pi. Theta plus 2 pi is basically just theta, effectively. It's the same thing, it's the same point, right? So this is effectively t of theta plus pi minus t of theta. We have seen this somewhere before. This is just g of theta. In fact, this is negative of g of theta, minus g of theta. So I am seeing that this difference function is effectively changing its sign. What does this mean? This takes us towards a beautiful application of mean value theorem. I am not going to state the mean value theorem. I will try to explain it intuitively speaking. What is the intuition here? So let us plot this function g as a measure of the angle, right? So let's say this point was theta. Let's say this point was theta plus pi. Assuming at theta, this g of theta, there will be two cases. This is case 1. Assuming that g at point theta was positive, let's say this value was something like this. At theta plus pi, this is exactly the negative of it. So let's say this is some value called k. Let's say some constant k. At theta, g of theta, let's say this value was some k. At theta plus pi, this particular function is basically minus k. So let's say this is minus k, but theta plus pi, this is minus k. Since the function is continuous, this has to at least cross over this axis once. Please note that it's not necessary to just cross over once. It can cross many times as well. So for example, it could be something like starting like this and be like this, something like this, and eventually reaching here. It cannot go back. This is actually wrong. Like functionally speaking, this is wrong. It cannot go back. So it's something like this, eventually reaching this. It can be like this also. But in any case, we are sure that there exists one such point, one such phi belonging to between theta and theta plus pi, such that at that phi, let's say this is phi, g of phi was 0. what that means is T of phi minus T of phi plus pi was 0, or T of phi was T of pi plus pi, which means the temperature was same on the two diametrically opposite points. Please note that this same thing, should I expand this for better visualization? I think I should do. Yes. So please note that in any other case also, let's say here it is crossing 1 times, 2 times, 3 times, 4 times, 5 times. So this would basically mean that there were 5 instances such that G became 0, difference became 0, or temperatures were equal. In other words, on that particular circle, there were 5 such pairs, 5 such points, diametrically opposite points, 5 such pairs of diametrically opposite points, such that their temperature was equal. But that is like some other random case. Worst case, like at least there has to be one such pair, because it is a continuous function which was positive here, which is exactly the negative at theta plus pi. It must cross the x-axis once. We can now, anyone who is watching this video can think what will happen in the negative case as well. It's just the opposite of it. So this is G, this is theta, this is theta plus pi. So let's say at G of theta the value was negative, so minus k was here, and plus k is being attained here. In that case also, since it is continuous, it has to cross over, and when it is crossing over at some particular angle, the difference is 0, or in other words, the temperature is same. Hence, we have proved that there exists some theta such that these two temperatures will be equal. I would say this is quite a beautiful problem. And if someone wants like the name of the theory behind this, it is mean value theorem. So people interested can go ahead and read about it. So it is a general theorem, so to speak. It will state if you have a continuous function from a range A to B, then the mean of that function must exist at some point. So people can go ahead and study more about mean value theorem as well. But I wanted to give a more intuitive explanation, more common sense and logical explanation without throwing theorems into the picture, so that we could understand uh, how beautiful this problem is. So that's all for this problem. I hope this was interesting, this was helpful, at least this was fun for people who already knew the solution of the problem as well. Uh, that's all for this video. Thanks for watching. If you like my content, consider liking, sharing, and subscribing to my channel. See you in the next one. Thank you.